Okay, let's talk about curve sketching. So curve sketching is this method where you put all your information in tables and it helps you decide what the graph would be, where the mins and maxes would be, where there would be a change in direction, all of those types of things. And it's typically you're learning about this at the same time that you're learning about optimization problems or even related rates problems, maybe not as related, but anytime that you're trying to maximize or minimize or figure out where the directions of graphs are changing or when you're accelerating or when you're not accelerating, those types of things. Okay, the intervals on which you're doing those things. So the first part, for each problem, find the x coordinates of the critical points, the open intervals where the function is increasing or decreasing, x coordinates of the inflection points. Okay, so this first part right here talks about the increasing and decreasing sections, right? So right here we have a negative x cubed, a negative cubic. So what that is saying is where will the intervals be where the graph is decreasing, increasing, and decreasing? And it should look about something like that because it's a negative cubic. But in order to find those intervals, you have to find the critical points. And the critical points are the mins and maxes, right? This would be a critical point, and this would be a critical point. So you find those by taking the first derivative. So we're going to bring that 3 down in front, and that would be 3x squared. So that will be the 3 and the 12 cancel. So that is negative x squared over 4. And then when you take the derivative of negative x squared over 6, the 2 comes down. And then that becomes, you know what? I'm going to, for the purposes of factoring in a second, I'm going to leave it as negative 3x squared over 12. And I'm going to leave this as negative 2x over 6. In fact, I'm going to want these to have the same denominator, so I'm going to multiply this top and bottom by 2. And so I'm going to rewrite that as negative 3x squared over 12 minus 4x over 12. And I'm going to set the derivative equal to 0. And I'm going to factor out, they both have an x in common, and they both have a 1/12 in common. I'm going to factor out a negative 1/12. So negative 1/12 x, we factor that out, we get 3x plus 4, right? Because when we factor out, when we factor out the negative, negative divided negative is positive, negative divided negative is positive. All right, so this first x right here, on the outside of the parentheses, x will equal 0, and x will equal negative 4/3. So on the number line, I already have the number line. As you read left to right, negative 4/3 comes first, and then 0 comes second. And what we're looking for, what's happening on the intervals? Well, if you sketch the graph, you should be able to see this one should be decreasing, increasing, decreasing, but you still have to use the derivative test. So I'm going to pick a random number, so I'm going to pick negative 10 to plug in there. Negative 4/3, that's a little bit more negative than negative 1, so I'm going to put negative 1 there, and I'm going to go ahead and put 10 there. So when I plug negative 10, and I'm going to use this part of the derivative, the factor part, well, negative times negative is a positive on the outside of the parentheses, and then negative 30 plus 4 is negative. Well, positive times negative is negative. So this is decreasing, right? So on the interval from negative infinity up to negative 4/3, and I'm going to change that color because red is not a great color sometimes. So you put the 3 kind of diagonal down arrow keys, and then we go ahead and make sure to put the word decreasing. Okay, now we're going to try the new interval, so negative 1. Again, negative times negative will be a positive on the outside. Then 3 times negative 1 is negative 3, but negative 3 plus 4 is positive. So positive times positive is positive. So your 3 plus signs, and this is increasing. So from negative 4/3 up to 0, the graph is increasing. So what that means, because it went from decreasing to increasing, where x is equal to negative 4/3, that is a critical point. So you're going to plug negative 4/3 into the original function. So let me go ahead and erase that so you remember what the original function was. And I'm going to go ahead and let you do that on your own. Remember, when you do that, put a negative sign on the outside parentheses, and then negative 4, divide 3, or fraction 3, right parentheses, caret 3 for cubing, and then subtract parentheses. And then that's going to be, and I'm sorry, and that's over 12, and then subtract, and then this is going to be over 6, but inside there we have negative 4 fraction, or divide 3 squared. So type all that in and you're going to get that height right there. Okay, and just by looking at the graph, that should end up being the relative min. I'm just not going to take the extra time, and I didn't put my calculator next to me, so I'm going to let you come up with that height. All right, now we're going to do this interval. So we're going to put positive 10. Well, negative 1/2 times 10 is a negative on the outside of the parentheses. And then 3 times 10 is 30 plus, so that's going to be a positive, because 30 plus 4 is 34, positive 34. So we're back to negative times positive is negative. So we're back to decreasing. So from 0 to positive infinity, we're back to decreasing. So that means where x is equal to 0 is another critical point. Remember, this is the critical point column. And so when you plug, 0 is easy. When you plug in 0, 0 subtract 0 is 0. And that will be a relative max. I could be wrong, so you still need to check it. There we go. All right. So pause this if you need to write all the stuff down, because I'm going to erase much of this. All right, so I'm going to erase this part because now we have to talk about concavity. Okay, so here's the derivative, the first derivative right here. Well, to talk about concavity and to find the inflection point, remember the inflection point is the point where it right at the exact moment that it changes from being concave up to concave down. Okay, and that's the point where you find intervals of acceleration also. Inflection point, right here, if it's positive, you're speeding up. If it's negative, you're slowing down, that type of thing. So, all right, so you find the second derivative. Well, negative 3/12 x squared, you bring the 2 down, and that would be negative 6 x over 12, and then subtract 2/6 is negative 2/6 is the derivative of negative 2/6x. And then let's see, I'm going to multiply again top and bottom by 2 so that the denominators are the same. So that's going to be 4/12. I'm going to set the derivative equal to 0, and they both have, I'll just factor out a negative 1/12 again, but this time they don't share an x, so it's just negative 1/12, and that leaves 6x plus 4. Notice we could have factored out a negative 2/12, which is negative 1/6, and then this would have been 3 and this would have been 2, but it's okay. This x right here is going to be negative 4/6. That simplifies to negative 2/3. And if you'll notice, halfway between the critical points, halfway between 0 and negative 4/3 is negative 2/3. So then we're going to pick an interval over here, an interval number. I'm going to pick negative 10. And to the right of a negative number, the easiest one is 0. So and let's see, so our intervals will be from oops, I'm going to change that back. Negative infinity to negative 2/3 and negative 2/3 to positive infinity. All right. So when we plug in negative 10 into the second derivative, well, that would be negative 60 plus 4 is a negative number, and this is a negative number on the outside, so negative times negative is positive. So this is concave up, and this is what you draw that, and I'm going to put the word up right there. So for the concavity, you draw the upward looking parabola with the 3 plus signs, and then I'm going to plug 0 into the second derivative. Well, 6 times 0 is 0. 0 plus 4 is, there's a positive on the inside, but there's still that negative 1/12 on the outside of the parentheses, so that's negative. So it's going to be a concave down. So where x is equal to negative 2/3 is going to be the inflection point, and you're going to find the complete xy value. So it's negative 2/3, and then you take your negative 2/3 and you put it back, you substitute it back into the original function, not the derivative, but the original function, to find that height. And then once you have all that information, it's pretty easy to graph, to sketch a graph. So let me go ahead and do this. If you need to put it on pause because you need to keep writing stuff down, go ahead and do that now because I'm going to graph this. Okay, so actually I'm going to pause because I'm going to need those two heights. Okay, I did not go get my calculator because I don't know where it is, and I'm not going to go ahead and take the time to do that by hand, although it's not really all that difficult, but I'm going to quickly do this. So you have negative 4/3 at a certain height, and when we put in negative 4/3 up there, it's probably going to be a very, very small number. And look at, that's going to be a relative min, and 0, 0 is a relative max. So that, and the graph looks something like this, right? So we're going to come down. It's actually going to, I'm not doing this very well at all. I'm not doing that very well because it doesn't touch the x-axis at the negative 4/3. Oops. All right. So it's going to come down like this. It's going to peak. It's going to have a maxima right there and then start to go back up and look something like that. So halfway, it would have been coming from over here. So halfway between negative 4/3 at the minima and at the maxima, 0, 0, right there at about negative 2/3 is that inflection point. So not a great graph. I should have just put it in Desmos and showed you the exact what it would look like, but you get kind of the general idea. And that's what it is to curve sketching. And that's it.